So physically, what is a capacitor? All right. Now, in the picture there, these are some examples of what's called Leyden jars. Okay, Leyd, I think A-N, it could be an O-N, I'm not sure. Jars, okay, and they are capacitors. Now, if we let's take any one of these guys here. All right, if we could get a close look at it, what we would see is it's a glass jar, like so, but then it has a coating of tin or aluminum on the outside and on the inside, like this. Okay, and what they used to do, and there'd be like a ball up here and a chain coming down contacting this, is if you put some positive charge here on the end, like this guy right here, then on the outside, okay, you could create a negative charge. All right, so you might, for example, connect this thing to a battery, okay, here and here, like this. And what that's going to do is it's going to create a voltage difference on both sides of that jar, and electrons, in this case, electrons are going to accumulate on the outside, and then those electrons are going to get moved out, and so you're going to be missing electrons on the inside, which is going to cause us to have a positive charge inside there. Okay, so they used to use these Leyden jars for studying static electricity, okay? And so when you are trying to generate static electricity, and we'll talk about this more after spring break, it's hard to store all that energy, okay? It goes away pretty quickly whenever you try to generate some static charge. A Leyden jar is a way to keep track of that, okay? Now, in modern times, okay, if you have a capacitor, these are all examples of capacitors. In modern times, a capacitor, if you look at a circuit, might look like this. It can be kind of a tiny beige thing, or maybe a bit more of a square thing with some wires out at the bottom. Some of them even are these cylindrical jobs with wires out either end, or maybe even like this. Okay, so they come in a lot of different forms, but no matter what form the component takes, ultimately you have the same basic design, which is you need two conductors, okay, here and here. All right, and then you're going to need some way to keep them apart. Okay, so you need some kind of an insulating material in there. That way you can accumulate negative charges on one side and positive charges on the other. Okay, now once you have these charges accumulated, then you can pull those back out if you needed to. Okay, so that's going to make a little more sense as we go along here, okay? But you could pull those out if you need to. Okay, now the amount of charge that you collect, Q, depends on how much voltage you put across this thing. So let's call that a delta V, okay? And so you can see our first equation there, Q equals C delta V. So this Q right here is the amount of charge that's on the jar, okay? And we're not too worried about how much charge is in a capacitor right now because we're more interested in things like current. All right, so we'll talk a little bit more about what that means to charge something and how that relates to electrons moving around. We'll do all that after spring break. Okay, but it depends on the capacitor value, okay, and then whatever voltage you put on there. Now, capacitors have a kind of a weird set of units. We use the symbol F because they're called farads, and they're named after a guy named Faraday, okay, sort of like that. A farad is a very, very large unit. Okay, it's a very large unit. And so most of the time when you see a number representing capacitance, like in an example or something, it could be anything from as small as maybe 5 picofarads, okay, which is going to be 10 to the minus 12 pico, all right, or maybe a really big one. I mean, a big one would be maybe 1,000 microfarads, okay, which is 1 millifarad. That's pretty big. Now, it is possible to purchase a 1 farad capacitor, but they're pretty expensive and kind of hard to come by. All right, but most of the time they're going to be picofarads, nanofarads, millifarads, microfarads, way down in that range right there. Okay. Now, when we're moving charge around, okay, it takes some energy to do that. Okay, and so moving these electrons, you've got to have a source somewhere that's creating a change, and then that change you can convert to the electron motion. All right, so that source for that change could be a chemical reaction. All right, so you've got an energy change in the chemical reaction that turns into your current, which is a change. Okay, you could hook this thing up to a bicycle and generate some electricity using your own body. All right, as the source for change, as the energy source, okay, sort of like that. And then we're not going to go through the derivation here, but we've got 2 different expressions down here for the energy. Okay, one is a half CV squared, and the other is Q squared over C. The Q squared over C version, you just substitute in here. All right, kind of like when we talked about power. We said power can be IV or I squared R or V squared over R. Those things, same kind of deal. You can just sort of substitute in there. Okay. Now, the reason, I got to get rid of some stuff here. The reason we use the model of a pipe that's got little bulgy ends on it. Okay. The reason we use that model of a pipe, the little stretchy ends, okay, is because in a circuit, okay, if we hook up our capacitor like this, okay, we're going to end up with extra electrons here. It's going to be negative on the backside and positive over here, like that. So putting those, removing electrons or adding electrons, so making it positive and negative charge there, what that does for us is that's kind of like stretching out that membrane on the end of our pipe, okay? And so if we decided for whatever reason that we didn't have an EMF in here and we connected our wires, then current would flow around here this direction like that, okay? So that stretched out bit would push all those things back around the other way, okay? All right, and also the reason that we're limited in how much current can flow is because as we accumulate these charges on here, the voltage on this thing begins to go up. Okay, and if we have got some voltage over here, eventually we're going to end up with that same voltage on our capacitor, and then you can't have any more current flowing, okay? Because it's like we've got the battery, which is an elevator up, but then there's like no way down, because on the other side is another elevator up. Okay, so we can't have any current flowing there. Now let's hit inductors while we're doing all this. Okay, an inductor is when you've got a coil, okay, sort of like this, and here's some different examples. And again, some of these components, if you were to see, I mean, they would look a little bit like a resistor. I kind of showed you a picture in class one day. They're a green color. All right, and they got little stripes on them. Okay, so those are also inductors. Those inductors that look like resistors, they're small values, okay? For these bigger things here, they have a larger inductance value, okay? And you can see they're literally coils of wire, and that's important because you probably know if you take and run electricity in a circle like this, it creates an electromagnet. Okay, so an inductor is kind of also like a teeny tiny little electromagnet sitting in your circuit. Okay, and what we're going to learn is that electromagnet property, all right, actually can create a voltage. Okay, and it does it with this equation here. All right, so if we have an inductor, and how much voltage it creates depends on di dt. So it depends on how fast the current is changing. All right. So this is kind of like, think about the propeller. All right. That's our model for this case. All right. I've got my pipe here, and it's like I've got this little propeller in here. Okay. So if all of a sudden there's a lot of water trying to get through there, a propeller that's not moving is going to have a big impact on it, okay? So if we try to change that current very rapidly, we end up having a big effect because of our inductor. Now, the inductors also are a way to store some energy, okay? And so we would have the value of the inductance, and it depends on how much current is flowing, okay? So, in a way, a capacitor, which is its energy was 1/2 C delta V squared, let's say. Okay. That's kind of like a compressed spring. All right. Kind of like a compressed spring where the capacitance would be the value of the spring constant and the voltage would be like how much you've compressed the spring or stretched the spring. Okay. If that's like a spring, an inductor is more like the equivalent of kinetic energy, okay? So L is kind of like mass. I mean, it's not mass, and just like C is not the spring constant, but it's a 1/2. It's kind of like 1/2 mv squared. So it's a half times something that's moving, okay? So the charge is moving, that's our current, okay? Sort of like that. But energy is represented or stored in both of these cases like that, all right? Okay, inductance values are all over the map, okay? They're always measured in henries, okay? So we might have, for example, mH, okay? That's a henry, also named for a great 19th century physicist there, okay, who investigated magnetism and stuff. Okay, and so those are all always going to be pretty small as well. Okie dokie. So now, inductance is the property of being kind of like an electromagnet. Okay. So that has to do with the fact that when you've got a coil, you've got a loop of wire, all right, it can kind of behave like an electromagnet, and that has implications for voltage. All right, so that's going to try and create a voltage. So that's the property of inductance. And an inductor has a specific amount of that inductance. Okay, like a resistor resists. It has the property of resistance to current, but the resistor itself has a particular amount of that resistance. We could say the same thing with capacitors. Okay. Capacitance is the ability to store charge. All right. And a capacitor is an object that can store charge with a specific value. Okay. Sort of like that. Occasionally, this is kind of an old term. You might see it, the term condenser. Okay. Sometimes like on a motor or something like that, you might see the word condenser. That means it's a capacitor. Okay. My microphone here is a condenser microphone. So it has a teeny tiny little capacitor in there. As my voice hits that thing, the capacitor is moving. back and forth, boom, 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 like this. And the motion of that causes a voltage change. And that then gets, turned into how you can hear my voice. Okay. All right. Now, that's it for this segment here. And so when we get into the next segment, we're going to be doing some differential equations work. Okay. If you've never had differential equations, don't worry about it. I'm going to tell you what you need to know and how it all works. Okay.